Welcome everyone to the last session of this first day of this Overfull workshop. And our speaker is Daniel Litt from University of Georgia, who's, well, at least the second version of the title is the one you see, Hodge, p-adic squared, I guess, or it's really p-adic times 2, I don't know, but and tropical iterated integrals. Okay, go ahead, Daniel.
All right, thank you for that introduction, David. And also it's really nice to be here. I really appreciate so many people coming to the talk at such wildly different times in the day for everyone. So I want to talk about a few different types of iterated integrals. So this is some version of iterated integrals in the Archimedean setting, like for over complex varieties. Then I'll talk about two different types of p-adic iterated integrals. So that's the squared, and then some kind of tropical iterated integrals and the relations between them. So in terms of the relation to this conference, the p-adic iterated integrals I'll be discussing encode through some p-adic Hodge theory Galois actions on fundamental groups. So at least that's my claim about the relationship to the conference, but that's all I'll say about Galois actions on fundamental groups. This will mostly be a talk about integration. And everything I'm going to say is joint with Sasha Shmakov, my student in the Archimedean setting, so the sort of Hodge iterated integrals, and then with Eric Katz in the p-adic and tropical settings. So I want to start by talking about the Archimedean setting. It's not strictly, like, it's not mathematically directly related to the rest of the things I'll talk about, but philosophically it's very closely related, and like many of the actual ideas involved in the arguments I'm going to describe are more or less the same. And then I also think, like, you know, iterated integrals in the complex or real setting around manifolds is something that's very familiar to everyone, like hopefully from, you know, when you took a multivariable calculus course a long time ago. And so I think, you know, we'll see a lot of the same things appearing in a kind of more familiar setting, although I'll still tell you some things that I think will be new even about this very elementary kind of operation. Okay, so let me start by discussing the situation and some examples and like what the problem I want to solve is. So the main issue that I want to discuss is that, like, line integrals and then iterated line integrals are not in general single valued. Oops, that's the wrong color. Are not in general single valued. So for example, suppose you take two non-zero complex numbers, a and b, and you try to integrate the one form dz over z over a path from a to b. So here, this is a path that has to lie inside of C star, and the answer you get is gonna depend on which path you take from A to B. So what you'll get is log of b over a plus some integer times 2 pi I. Okay, and this integer is going to depend on what path you take. It's more or less dependent on the winding number of that path around the origin. Okay, more generally, this is just a sort of ordinary line integral, but you can do the same thing with iterated integrals. So you can pick a path from A to B, and then do sort of an iterated integral. So you integrate from A to Z1, where Z1 is some parameter on the path. And here I've taken some one form, dz2 over 1 minus z2. And then you iterate that with respect to dz1 over z1. So this particular example gives you, well, the dilogarithm. Well, maybe let me not try to write down the exact expression, but it gives some expression here, which is a linear combination of, I think what one ends up is getting is some things involving the dilogarithm of b, the dilogarithm of a, some log of b over a's, and some, I think, 2 pi I squared when one does this. So and again, the coefficients of these various terms are going to depend on the path one chooses from A to B. So this is not a single valued iterated integral. It has some monodromy. Okay, so the problem is there a way of assigning to these expressions a kind of single valued function? Okay, and maybe this is a spoiler, but the answer is yes, or otherwise I wouldn't be giving this talk. So let me, before explaining that, let me kind of discuss exactly the setting in which one can hope for a single valued iterated integral. So suppose X is a smooth complex variety. For this slide, everything I'm going to say will be fine for any smooth manifold. But since for the rest of the talk, I'll use some mixed Hodge theory, I'll just work in the setting from the beginning. So I'll call A1 of X the space of C infinity one forms on X, so smooth one forms on X. And then I want to say, first of all, what it means for a linear combination of one forms and tuples of one forms to be homotopy invariant. So typically when one takes if one integrates a closed one form between 2 points, the answer depends on the path you take between those points, but it only depends on the based homotopy class of the path. And for iterated integrals, that's not true anymore. So there's this sort of extra conditions, and I'll discuss this a bit. But the simplest definition is, suppose you have some linear combination of n tuples of one forms or tensors of one forms. So I'll say that's homotopy invariant if the integral of a path along a path of this n tuple of one form. So if n is bigger than 1, that'll be an iterated integral. If this only depends on the based homotopy class of the path. So some simple examples of this are, well, if X is a Riemann surface, so all n tuples of holomorphic forms are homotopy invariant. So this follows from the fact that the cut product of 2 holomorphic forms is always 0 on a Riemann surface. And then another example is for X arbitrary. So even an arbitrary manifold, if you take a linear combination of one forms like this, so you have one which is kind of a monomial in 2 one forms, and then the other one is just one form. If this satisfies the condition that d of omega 1, 2 equals omega 1 wedge omega 2, then this n tuple of one forms will be homotopy invariant. So what I mean by that is that if you integrate this from a to b and then add it to the iterated integral of omega 1 and omega 2, you'll get something that only depends on the path. All right. Are there any questions about this so far? By the way, you should feel free to interrupt me if you have a question. I mean, this is an intimate gathering. All right.
What are you drinking?
I'm sorry?
Are you drinking beer? In your
no, this is it's early for me. This is seltzer. Yeah. Okay. So here's the theorem, and then I'll explain a bit more precisely what this means. So this is joint work with my student Sasha Shmakov. So suppose X is a smooth complex variety, and omega is a homotopy invariant linear combination of n tuples of one forms like before. Then the theorem is that there exists a single valued iterated integral. So what this means is there's a way of assigning to this omega a number and 2 points, a and b and x, a complex number. And that's a canonical assignment. And I'll describe some of its properties. Yeah, okay, so what do we get here? So first of all, this number varies real analytically in the endpoints. So for example, if you fix A and vary B, you get a real analytic function on your variety. Second of all, it's functorial. So if you have a map between varieties F, so here F has to be an honest algebraic map. Like the universal cover C to an elliptic curve doesn't work. Like it has to be defined by polynomials. Then one gets the following relation. So the integral from f of a to f of b of omega is the same as the iterated integral from a to b of the pullback of omega. Okay, and then finally, there's a sort of composition law, which, well, I won't read it out to you verbally, but it's exactly the same as the composition law for ordinary iterated integrals. So there's a formula if you go from a to b, if you integrate from a to b of some n tuple here, that's the same as doing something in terms of integrals from a to c and then integrals from c to b. So for example, if n is 1 here, if you only have one form, this just becomes the fact that the integral from a to b is the same as the integral from a to c plus the integral from c to b. Okay, so which is a very standard formula from the theory of integration. Okay, and then I've written a ... here. I mean, this has maybe maybe I'll just write it has many other properties. So for example, this one is something about composition of paths. There's also some relations between, if you take omega 1, omega 2, and then omega 3, omega 4, there's some relationships between the iterated integral of the 4 tuple and the 2 tuple. But I won't list them all exhaustively, but the point is that this operation has more or less the same properties of iterated integration along a path. And maybe it's worth noting, there are some related theories of single-valued iterated integration in the literature. So in particular in work of like Boleyn, and then more recently, Francis Brown. So as far as I know, this is the sort of the first theory that works for general smooth complex varieties. The previous theories are primarily about like unirational varieties. So for example, varieties where their H1 is pure of weight 2. Are there any questions about this statement? So I'll explain kind of what it really means in a bit. And I'll give some examples. All right. So let me give you. Yeah.
Which of the properties characterize the integral?
As far as I know, I don't know if these properties characterize the integral. I'll give a characterization later. So these are properties that it has. I would guess that collectively these characterize it, but I don't have a proof. Yeah, I think it's kind of an interesting question. All right. So here's some examples. So let's go back to the sort of very first example we looked at. So one can take the integral from a to b of dz over z, and here this little arrow through the integral means that I'm using this sort of single-valued iterated integral. And here's the answer you get. You get 2 times the logarithm of the absolute value of b over a, which is evidently a single-valued function. It's not holomorphic, it's just real analytic. And you can check yourself if you'd like that it satisfies the list of properties that I described earlier. Okay, a little bit more generally, you can take the iterated integral of dz over z tensor n. So this means you actually, it's like a genuine iterated integral, not just a path integral. And this is what you get. You get 2 to the n over n factorial times log n of the log to the n of absolute value of b over a. So this doesn't mean compose log with itself n times. It means the nth power of log. Okay, and in fact, this really just follows from a sort of general formula for what happens if you take the iterated integral of the same one form a bunch of times. So there's a similar formula for just standard iterated integration. And so this is sort of an example of one way in which this sort of single-valued iterated integral gives something kind of well-behaved. Okay, let's look at the next example. So here we have dz over 1 minus c and dz over z. These are one forms on p1 minus 3 points. And in sort of the usual complex setting, if you take the iterated integral of these one forms, you get a branch of the die logarithm. So this wants to be something like sum of z to the n over n squared. This is what it would be if you took the usual iterated integral. Okay, and here one gets some long expression I won't write down, but it's in terms of an object, a sort of well-known object called the Bloch-Wigner die logarithm. And it actually recovers the Bloch-Wigner die logarithm so as you take a to 0 and then throw away a term with log poles. You actually get the Bloch-Wigner die logarithm, which is this function I've written here. You take the imaginary part of a branch of the die logarithm and then add on to it the argument of 1 minus z times the log of the absolute value of z. So this is some expression discovered by Bloch and Wigner, which is meant to be a single-valued analog of the die logarithm, and it shows up in a number of arithmetic settings. And in fact, I mean, this example is the first in a long series of examples. So Zagier discovered a whole collection of single-valued versions of the polylogarithm, and one recovers all of them by doing this integral, and just instead of doing just two terms here, you do dz over 1 minus z, and then some n-1 tuple of dz over z's. So I mean, in some sense, this fact was already known due to work of, I think, Francis Brown, since sort of there's a special case of this theory of single-valued iterated integration I'm describing is due to him. So this is, maybe it's worth attributing this example to Brown. Okay, so the main benefit of this technique, of this tool here, is it works on kind of arbitrary smooth algebraic varieties. So in particular, the sort of next interesting example is you can do this on a elliptic curve minus the origin. And I won't describe the detailed setup because this is a talk on arithmetic, not complex geometry. But when one does this appropriately, one recovers something called Haynes elliptic dilogarithm for when one does a sort of double integral. So again, one is you're recovering sort of well-known objects. So I mean, the nice thing about this is that beyond sort of, I think, giving an explanation for what I view as like pretty magical formulas people discovered for single-valued iterated integrals in the past, like this I think clarifies a lot of the properties. So for example, a lot of one can deduce more or less all the functional equations for these special functions just using the functoriality of the single-valued iterated integral. All right, are there any questions about this?
Actually, maybe I'll ask something. That the top example, at least, what's going on is that the integral from A to B is the same as the integral from absolute A to absolute B. And so if you look at the non-zero complex numbers, you can view that as mapping onto the positive reals. And then you're really integrating there. And so then you're pulling back and the positive reals are simply connected. On the other hand, I see there's an argument in number 2, which of course means that's not happening. But right. Is there nevertheless some way in which this is really the integral on something simply connected, and then you're pulling back to whatever space you're on?
That's a really nice question. I mean, that's not how we think about it. But I do think that's actually very interesting. Yeah, I don't know. That's a really, really good question. Yeah, I don't know.
Okay.
Yeah. So I'll explain how we think about it.
Maybe.
Oh yeah, go ahead.
Maybe another. So similar to David's question, is this not, if you go to the universal cover, then maybe this, how does it behave under finite covers?
Yeah, so it's a good question. So first of all, the universal cover is typically not like an algebraic map. So there's no functoriality with respect to the universal cover. Like we actually really use the mixed Hodge structure here. And so, yeah, but with finite covers, I mean, everything is algebraic. So everything is nice and functorial. But yeah, you somehow can't compute on the universal cover because like there's no Hodge structure on pi1 of the universal cover, which is just trivial. So somehow one can't even make the definition.
So the point is, the question is whether you can take inspiration, what you have to do from the universal cover. Yeah,
it's a good question, and I don't know how to do it. I mean, somehow I think like the sense in which the Hodge theory of pi1 is related to the Galois action on the the pi1 action on the universal cover by deck transformations is like kind of mysterious to me. So if you understand that well, that would maybe be the answer, but I don't understand that well enough to tell you. Yeah. All right, so let me just describe one more corollary. I think this must be known, but I wasn't able to find it in the literature. So suppose you have a smooth complex variety and a unipotent flat vector bundle on it. So that's a vector bundle with a flat connection such that it's an iterated extension of vector bundles of the form O with the trivial connection D, well, maybe I should call it delta, the Drame differential. Then the theorem, I mean, or the corollary of this construction is that there's a kind of canonical functorial real analytic trivialization of this vector bundle. What I mean by that is that if you choose a point X there's a sort of canonically trivial real analytic vector bundle just given by the fiber of your original vector bundle over your point. And there's a canonical isomorphism between the real analytic vector bundle underlying E and this kind of canonically trivial real analytic vector bundle. And why is that? Well, it's just because you can parallel transport. And the single valued iterated integration gives you a canonical parallel transport. So canonical isomorphism between any fiber of this and sort of the fiber at X. So I mean, that's sort of silly. Like once you realize this, you can actually just prove this by hand using Hodge theory. It's not that hard, but it somehow, I never noticed this before, and I think it's kind of cool. Okay, so where does this come from? So the reason I wanted to spend so much time on this Archimedean setting is that the idea is like the reason I kind of noticed this is because of thinking about some things that happen in the p-adic world, but I think this is like a nice way to kind of become comfortable with the objects involved before diving into the p-adic stuff in the second half of the talk. So let me just briefly describe the idea of the construction. It's to use the mixed Hodge structure on the unipotent pi1 of X. If you haven't seen this unipotent pi1, I'm going to kind of give you a very concrete description of everything now. So first of all, so remember X is a smooth variety, not necessarily projective. And we're going to start by looking at two different vector spaces. So one is just the group ring of pi1 of X with some base point. So this is going to be the group ring of pi1. Okay, and then here you can take if you have two different points, X and Y, you can take the free vector space on the path torsor. So that's just the set of homotopy classes of paths between X and Y. So inside of this group ring, there's a natural ideal, the augmentation ideal. So what's the definition of this? Well, there's a natural map from this group ring to C, sending every element of the group to 1. And this is the kernel of that map. So equivalently, it's generated by differences between two loops. And then what we can do is we can just complete these vector spaces at the augmentation ideal. So here, the group ring is a ring. You can take the completion at the augmentation ideal. Okay, and then this sort of second, and here I'm denoting this with double brackets. So you're supposed to think it looks like a power series ring, kind of. And here I'm going to describe the situation with the path torsor. So how does one complete the path torsor at an ideal? Well, this vector space here is a rank 1 free left module over this ring. Because if you have a path between X and Y, you can just compose it with a loop at X. And so if you have a module over a filtered ring, the module acquires a filtration, and you can complete it that filtration. So this is just the same thing. It's, again, the completion at the p-adic filtration. And these are typically pretty concrete objects. So for example, if X is a non-compact algebraic curve, its pi1 is a free group, and this is just a non-commutative power series ring in the number of generators. I mean, abstractly. And then this is just a rank 1 free left module over that. Okay, and then it's sort of not obvious, but at this point well known, that this ring acquires a lot of extra structure. So in particular, it has a natural Hodge filtration. And weight filtration. Making it into a mixed Hodge structure. Well, both this ring and this module over it are mixed Hodge structures. So where do those come from? Well, this weight filtration is defined pretty combinatorially. So for example, if X is a smooth proper curve, the weight filtration is just the p-adic filtration. If there's punctures, you slightly adjust that in terms of a simple normal crossings compactification. And then the Hodge filtration is more or less defined in terms of iterated integrals. So it turns out it's a theorem due to Chen that the topological duals of these vector spaces are precisely given by homotopy invariant iterated integrals, which we discussed before. And then there's a sort of obvious filtration on those given just by counting dz's. So just like the usual Hodge filtration, when you write down the Hodge filtration on cohomology, you're just counting the number of dz's showing up in your one form. And you can do the same thing here on the space of homotopy invariant iterated integrals. Okay, so that was my verbal introduction to the mixed Hodge structure of pi1s. If you haven't seen it before, it doesn't really matter. All I'm really going to use is some abstract properties of this mixed Hodge structure. Okay, so the proposition, which I mean, I don't really know if I think maybe I should attribute this to Deline or somebody. Like it's not really written down anywhere except in my paper with Sasha, but well, the idea I think kind of goes back to Deline, is that there's a unique element of this space of paths. So if you'd like, you can think of it as some kind of virtual path between x and y, satisfying three conditions. So first of all, this element is one mod the augmentation ideal. So just like a real path, an honest path, it's one mod the augmentation ideal, same with this element. Second of all, this element is in the 0th piece of the Hodge filtration. So the Hodge filtration here is indexed by non-positive integers. So the 0th piece of the Hodge filtration is the smallest piece. This already pins down the path in lots of cases. So for example, if you take p1 minus a bunch of points, these two conditions already pin down the path. And I think this was observed by Brown and a number of other people in the past. Okay, and then here you have this, I wrote down, I didn't try to fill in the blanks here because I knew I would never remember the indexing. So here you take the complex conjugate of this path, meaning this elements of this are linear combinations of honest paths, and you just conjugate all their coefficients. And then you ask that it live in this infinite intersection of pieces of the Hodge and weight filtration. So this is some sort of magical condition. Okay, so that's the definition. There's a canonical path. It's really a canonical C-linear combination of paths, but you can kind of think of it as an honest path. It behaves just like an honest path. And here are some facts about it. So first of all, the path from a point to itself is just the constant path 1. So if you think of it as an element of the group ring, 1 is the constant path. Second of all, this path is functorial. So the push forward of this path is the same as the path between the images of the endpoints. So why is that? It's just because maps of varieties induce morphisms of mixed Hodge structures on pi1. And then the path from x to y, composed with the path from y to z, is the path from x to z. Okay, and then there's one can write down lots of other properties. So maybe I'll just verbally say one since it's morally important, although I won't ever mention it again. This vector space is a coalgebra. It has kind of a co-multiplication on it. And honest paths are group-like. The co-multiplication sends an honest path p to p tensor p. And the same is true for this canonical path. So that's another way it sort of acts like a real path. All right. Okay, now you can kind of guess, I think, what the single valued version of iterated integration is. So the definition, so suppose you have 2 points A and B and one of these homotopy invariant in one forms, then the definition we give for this single valued iterated integral is you look at the path from A to B, you take its complex conjugate, and then you integrate omega along that. Okay, so what does that mean? That means this is a linear combination of paths, and you just take the linear combination of iterated integrals. Okay, so maybe just a word. So why the complex conjugate? So why this complex conjugate of PAB rather than just PAB? I mean, so the reason is that there's two canonical paths. There's P and its conjugate. So typically we're interested in integrating holomorphic one forms. And if you integrate holomorphic one forms along the usual P, you always get 0. That's just the same as this fact. Or it's not quite the same. It follows from this fact. So to get actually interesting integrals, you need to choose the conjugate. Okay, so that's my justification for this choice of using the conjugate path. Okay, and I mean the bottom line here is, I mean, this is a definition. I think it has good properties. It gives you a lot of classical special functions and a lot of new and interesting special functions, but it's also like totally computable. It's really not bad to work out examples, and we do work out a lot of examples. So I think it's really cool. All right. Are there any questions about this before I kind of start discussing the p-adic setting? No?
So just concerning just the case of dz by z.
Yeah.
Actually, more or less, this says that actually the closed paths have value 1.
That sorry, value 0.
1, 0, 0. Yes.
Yeah, that's right. Yeah.
Is it not so that actually, if you could do everything for the closed paths, you would know in general what to do?
No, so what this says is, this fact here says that doing the integrating around a loop will always give you 0. So namely, the path from a point to itself is just the constant path. So, but I think that's sort of what you would expect for a single-valued theory of iterated integration. Like there's an obvious canonical path from a point to itself, and
yeah, so it's clear.
Yeah. Yeah. Cool. Any other questions? Yeah, so I think this is really fun. I mean, so the way I'm giving this talk is kind of backwards historically. Like I sort of started thinking about this after the p-adic setting, and it turns out that a lot of the ideas from the p-adic setting just work in Hodge theory more or less. Sorry, Michael, you've unmuted yourself. Did you have a question? No? Okay. All right, so let me start talking about the p-adic setting now. So I think most of what I'm saying would probably go through for arbitrary smooth varieties over a p-adic field. I'm going to limit myself to the case of curves because that's what we've checked carefully. So X is going to be a curve, meaning a smooth connected curve, over K, which will be a p-adic field. So first of all, let's consider the case where X has good reduction. So then there's a sort of analog of complex iterated integration called a Coleman iterated integration. And there's no problem to solve in the Coleman case. So Coleman iterated integrals are single valued. And that's because just like in this sort of complex setting I described, there is a canonical path between any 2 points. There's a canonical sort of Frobenius invariant. So canonical Frobenius invariant path between any 2 points. And here I've put scare quotes around both Frobenius invariant and path because, well, it's obviously not like a literal path in your p-adic curve. And there's no Frobenius action on the curve because it's over a p-adic field, not a field of characteristic P. But I'll describe what I mean by this in a little bit. So the interesting analog of our situation in the p-adic world is the case where your curve X has bad reduction. And then there's a theory of iterated integrals due to Berkovich, but Berkovich iterated integrals are not single valued. And that's almost by definition. They depend. So they depend. So here you have 2 points on your curve. You can look at their reductions in, let's say, a semi-stable model of your curve. And they depend on a choice of path in the dual graph of the reduction. So these are, they're path dependent just by definition. Okay. So I'll explain sort of where the actual problem comes from in a little bit, but this is sort of the situation. So what Vologodsky observed a few years ago is that there does exist a sort of canonical path between any 2 points. On X, I mean, again, this path should really be in square quotes. And it's defined in kind of a complicated way. So it's not just Frobenius invariant. There's another extra condition. And it's quite analogous to what we saw before. So earlier we saw that the sort of canonical path in the Archimedean setting was pinned down by some condition on the Hodge filtration and then some condition on the complex conjugate. of the path. And here we're going to have to, again, use some extra structure on pi1 to pin down the canonical path. So the question Eric and I wanted to understand is, so how do you compute this path and how do you integrate along it? So that's something, as far as I know, that hadn't really been worked out before. So in particular, this theory of Berkovich integration is pretty computable, at least in an abstract sense. I don't know. There are probably people here who know a lot more about how to compute it than I do. But so what we wanted to do is we wanted to write down this Vologodsky integral or integrals along this Vologodsky path pretty concretely in terms of Berkovich integrals. Okay, so the answer is going to be it'll be in terms of another kind of iterated integration. So the answer will be in terms of a so-called tropical iterated integral. So I'm going to describe to you a sort of purely combinatorial version of iterated integration that mediates between Vologodsky integration, which is single valued, and Berkovich integration, which is not. Okay, so I'm going to have to describe like a lot of structure on pi1. So what you should think is that this is like the p-adic analog of the structures that exist on pi1 of an Archimedean curve. So here's the setting. So X is going to be a curve over the ring of integers of your p-adic field, okay. And I'll assume it's semi-stable with smooth generic fiber. So there's two types of pi1. One can associate to this, well, there's a lot more types of pi1, but there's two types of pi1 that will be relevant for this talk that one can associate to this curve. So the first one is the log crystalline pi1. And I've written a lot of symbols here, so let me walk you through them. So really one takes the log crystalline pi1 of the special fiber. That's an algebraic group, and you can take the topological dual of the functions on it. Okay, this is some gadget, and what it gives you is something that looks a lot like what we had before. So this is going to be a non-commutative but co-commutative Hopf algebra. And for example, if X is a smooth curve with some punctures, this is going to be abstractly isomorphic to a non-commutative power series ring over the fraction field of the bit ring of the special fiber. So it's something that's designed to look like just like what we had in the complex setting. This ring has two endomorphisms. So phi, which is the Frobenius, and then n, which is the monodromy operator. So these are the sort of structures that exist on log crystalline cohomology and also on the log crystalline fundamental group. It also has a weight filtration, which is again more or less combinatorially defined. Okay, and then there's some compatibility, which is important for the theorems I'm going to discuss, but I'll just say what it is. So what it is that if you take the associated gradient of the weight filtration, the degree I piece satisfies the weight monodromy conjecture. In weight I. So namely, it looks like what we expect the log crystalline cohomology of the reduction of a smooth proper thing over a p-adic field to look like in degree I. So this is some linear algebra condition on how phi and n interact. All right. So the other, so you should think of this as maybe being analogous to just like the group ring or the completed group ring of pi1 of a curve in the complex number situation with no weighted or Hodge filtration. Just thinking of that as like the group ring of a discrete group. So that's at least the analogy I have in my mind. So the other, and this really only depends on the special fiber. So the other piece of data we have is the so-called Theorem fundamental group. So here you take the group associated to the category of unipotent flat vector bundles on the generic fiber of your curve. This is again a pro-unipotent algebraic group, and you can take the topological dual of the ring of functions on it. This is now a non-commutative but co-commutative Hopf algebra over K, your p-adic field. And again, just like in the complex setting, it has a Hodge filtration and a weight filtration. And there's not really much compatibilities between these except kind of numerical ones. Okay, and then finally there's a relationship between these two things. So if you take the log crystalline object and tensor it over the fraction field of the vectors of the residue field with a ring called KST. This is really just a polynomial ring in one variable over K. This is canonically isomorphic. Sorry, that's right. This should be the log crystalline one. This is canonically isomorphic to the same thing, except the DRAM version. Okay. Okay. So from this point of view, what is iterated integration? So let me tell you.
What was KST? So
KST is this is just this just means you pick a branch of log basically. So this is K adjoin log of a uniformizer. So this is the kind of comparison theorem you have between log crystalline cohomology and DRAM cohomology, the special fiber in general. So this is like more or less due to Hyodo and Kato. You should think of this as just being analogous to the fact that like Betty cohomology tensored up to C is the same as DRAM cohomology tensored up to C, or algebraic DRAM cohomology tensored up to C. Yeah, so this KST, I mean, if you make a choice, in fact, you can do this just over K, but this KST is saying that there's a choice involved, namely a choice of the branch of logarithm. Okay, so from this point of view, what's Coleman integration? And maybe I should say before diving into this, that this is like a totally backwards point of view on Coleman integration. But like, because, you know, I only have an hour to give you a talk, I'm gonna give you like the fastest way of knowing I know how to describe what Coleman integration is, like in terms of these sorts of fancy objects. So like, actually everything I'm saying is totally rigorous as a description of Coleman integration, but like you would never use this description to actually compute. Okay, so what happens?
All the time, so X is a curve, yes?
Yeah, X is a curve for now. Yeah. I think everything I'm going to say will be fine for just general semi-stable varieties with simple normal cross-distance compactification. But let me just work with curves. I mean, from the point of view of integration, you can always pull back to a curve anyway. So, all right. So suppose X is good reduction. Let me maybe just to be safe, let me write curve. So then the proposition, which I don't exactly know who this is due to, maybe Coleman. At least in principle, it's due to Coleman, is that there's a unique element of what I call the crystalline path torsor. So this ring, or really if X is not equal to Y, this vector space, it's a vector space over the fraction field of the vectors of the residue field, satisfying two conditions. So first of all, it's an element of this space. This space has a weight filtration. And I would like this element to be 1 modulo the negative first piece of the weight filtration. So this is just like before. My path was 1 mod the augmentation ideal, and this is just saying that this looks like an honest path. All paths have this property. And then second of all, there was this Frobenius action on this vector space. So phi acted on this vector space, and I would like this path to be fixed by that Frobenius action. Okay, and so Coleman observed, or at least ahistorically, Coleman observed that there's a unique element of this vector space satisfying these two properties. And this really just follows from the theory of weights on H1 of a curve. This is not, there's no more content here than sort of the fact that Hyodo-Kato cohomology is a well-behaved theory with a good theory of weights. Okay, and then well, to integrate, we need some one forms showing up. And the observation is that there's a canonical isomorphism between, when you look at the DRAM side, some piece of the Hodge filtration of this vector space intersected with some piece of the dual of the augmentation ideal, and the following. So this is just the same as H1 of xk omega 1 to the tensor n. So these are n-tuples of holomorphic one forms, if you'd like. If I don't assume X is proper, I should put a log D there, where and this I should work with the compactification, but maybe let me just for everything I'm going to say works fine without properness, but maybe just for simplicity of exposition, let me just assume properness. All right, so now suppose we have an n-tuple of 1 forms. So we can view that as living, this is some function on pi1. And here, this was duals. This was the dual space of functions on pi1. So if I have a path and an element of the dual space, I can pair them. And this is what Coleman integration is. It's just you take this canonical path, pxy, and you pair it with your n-tuple of 1 forms. Okay, so this is like an absolutely ridiculous definition of Coleman integration, but it is equivalent to the usual definition, not obviously. So for example, this would be like defining iterated integration in the complex setting using the comparison between the Betti and Theorem fundamental group. Like, of course, that comparison is defined in terms of integration, but you know, if you have a sort of iterated integral free proof of this comparison, which one can actually write down, this gives you an alternate definition of iterated integration. All right, are there any questions about this?
So here you don't have an analog of the complex conjugation acting.
That's correct. Yeah. Yeah, but I mean somehow already Frobenius and this weight property already pin down a canonical path. So you're already have a single.
I understand.
Daniel?
Yeah.
How does this relate to how Amnon Besser explains Coleman integration?
I would say, I mean, all the theories of Coleman integration are kind of equivalent. So this is, I think, a different point of view from what Amnon writes, but I think it's equivalent. I like this because it's a little softer, like there's vector spaces floating around, rather than like trying to work directly with unipotent bundles. But of course, it's in the background, since to define this object, one needs to work with unipotent, you know, a category of unipotent coefficient systems.
Mm-hmm.
Yeah.
So how does it depend on K? Does not depend. Yes, you could go view everything of the algebraic closure of K.
Yeah, you can always. I mean, yeah.
So this is invariant under.
That's right. Yeah. I mean, here So for example, you could say potentially good reduction if you wanted, and then extend. Yeah. Great. Okay. So what's Berkovich integration? So now suppose we're no longer in the good reduction case. So suppose you have a semi-stable curve, and let's take the dual graph of the special fiber. And it turns out this is not obvious, but there's a canonical specialization map from the fundamental groupoid of X to just the group ring, or the completed group ring of pi1 of this dual graph. And this surjection, I mean, this should be kind of familiar, like in the complex setting. If you have a degenerating curve, pi1 of the general fiber surjects onto pi1 of the dual graph of the special fiber. Okay, and this map is a canonical section just given by the Frobenius, or maybe let me write it as the phi invariance. Oops. So what I mean is that if you restrict this map to the Frobenius invariant subspace here, you get a bijection. Okay, so now suppose I have a path over here. That means it has a canonical lift over here. So if I have a path in the dual graph, I get a canonical element of this vector space. So, and what can I do? Just like before, I can pair it with a 1 form. Okay, so this is kind of why Berkovich integration isn't single valued. It's because, well, when gamma is just the trivial graph, when X has good reduction, this is just a one-dimensional vector space. So there's only one path. But in general, if gamma is some complicated graph, this is some kind of high-dimensional vector space, infinite-dimensional vector space, in fact. And there's lots and lots of paths, and for each choice of path, you get an integral. All right, so how do we solve this problem? So Vologodsky discovered that despite this indeterminacy, there's actually a canonical element of this vector space. So there's a canonical path. So here's what it is. So first of all, just like before, you ask that it be 1 modulo the negative first piece of the weight filtration. You ask that it be Frobenius fixed, just like the Coleman path. And then, okay, remember this vector space had a monodromy operator on it, and you ask for this complicated condition with respect to the monodromy operator. So for all positive integers n, the nth power of the monodromy operator applied to this path lives in some piece of the wave filtration, the negative n minus first piece of the wave filtration. Okay, so this theorem is more or less linear algebra. So it follows from the fact that this vector space, the weight graded, associated gradient of the weight filtration on this vector space satisfies the weight monodromy conjecture. All right, so what's Vygotsky integration? Well, you have this canonical path, and you integrate against it. Okay, so that's it. Okay, so now the question Eric and I wanted to understand is, well, how do you compute this path? And of course, the actual content is here. So you have to understand, all powers of this monodromy operator. And the monodromy operator is kind of complicated. Like it's this, at least we found this was, a little bit involved to work out. Maybe let me just, before diving into it, let me just briefly point out, like this really looks a lot like the Archimedean setting. So this is analogous to being 1 mod I. This is supposed to be analogous to being in the 0th piece of the Hodge filtration. And then this n to the n looks like the third condition we wrote down, or it's supposed to. I mean, in fact, that's how I guessed the third condition that I wrote down earlier. I stared at this really hard and then tried to turn it into Hodge theory. So yeah, maybe just a sort of crazy slogan that I learned from Francois Charles. So Francois told me at some point that all complex varieties have bad reduction, or have totally degenerate reduction, and so somehow the Hodge structure on a complex variety is supposed to be some analog of the Frobenius action and monodromy action on its cohomology. And
by the way, in terms of that, it's sort of like what comes up in Arkelov theory, because from the point of view of Arkelov theory, if you're looking at the infinite prime, it's as though it's got infinitely bad reduction.
Yeah. It's a really beautiful analogy, and I somehow, yeah.
But by the way, I guess one thing I should mention is in terms of the timing, because it looks like you've got 5 more pages.
Oh yeah, I will not talk.
So okay, yeah, I just wanted to point that out.
Yeah.
Okay.
So it ends at 4:30, right?
In principle, after questions, but anyway.
Okay, then I'll wrap things up. I'm almost done. Okay, so the question is how to compute this canonical path, and the answer is in terms of these tropical iterated integrals. So maybe rather than, I won't say anything about the proof because I'm running low on time, but let me just give the statement. So suppose you have a graph. There's a notion of a harmonic one form on the graph. So here I've written it down. You just take a function on the oriented edges. So what that means is you assign a value to each edge with an orientation. And then for each point in the graph, you want the values on the outward oriented edges to sum to 0. So this is like the combinatorial analog of a harmonic one form. So for example, this tells you that if you take an edge going this way, the value on that edge has to be minus the value on the edge going this way. All right, and here's some complicated definition, which actually turns out to be not that complicated. So how do you define an iterated integral of a bunch of harmonic one forms on a graph? Well, so first of all, suppose you take an honest edge and an n-tuple of one forms, then the iterated integral is just the product of the value of the one form on your edges. And now suppose you take 2 paths. Well, it's an inductive definition. So we know how to integrate along edges. So if I have a formula for how to write down the integral along the composition of 2 paths in terms of the integral along the paths, then we win. Okay, and here's the formula. It's just the same formula I wrote down earlier for the iterated integral along the composition of 2 paths. So here, I mean, how do you actually compute? You write your path as a composition of edges, and then you write down this complicated formula. Okay, and then here's the theorem. So under this canonical identification between the Frobenius fixed part of pi1 and the fundamental group of the dual graph of the special fiber, this Vygotsky path is the unique linear combination of paths, so that if you integrate any n-tuple of harmonic one forms along it for n bigger than 0, you just get 0. Okay, and it turns out there's a unique such path. So this pins down a unique element here. And And then I will end the talk by saying that what's the proof idea? Well, you have to reinterpret the tropical iterated integral in terms of the monodromy action. So that the action of this n on the log crystalline pi1 of your variety. All right, and that's, I think, everything I wanted to say.
Okay, thanks. Does anyone have questions?